Well, I think it's time, so we can start. Well, hello everyone, and welcome to the third session of the ISRM Young Members Seminar Series. I hope you are listening me okay. And well, my name is Ignacio Perez Rey, and Jennifer Day from Queen's University, Canada, and me from the SEM, the Spanish National Group from the ISRM. As part of this ISRM Young Members Group, are happy to chair this third monthly seminar. It is, of course, a great pleasure for us to be here today. And we would like to thank you for attending this third session. Well, before starting, we would like to thank the support from the International Society for Rock Mechanics and Rock Engineering, and especially to Sevda Dakota, ISRM Vice President for Australasia and Chair of this ISRM Young Members Committee. Thanks, Sevda. And we also would like to thank to all young member representatives of national groups that have joined this initiative from Spain, from Australia, New Zealand, Japan, Chile, and Canada, among others. And finally, we would like to thank Dr. Kimie Susuki and Mr. Alexander Ramos for agreeing to present their work in this session. Thanks to all. Well, before our speakers begin, we will take a moment to present some key information about the seminar series. Well, first of all, what are the ISRM-YM seminars? This project attempts to promote youth community interested in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community and to share experience both in the industry and the academia, and to strengthen relations between different countries. We would like to invite a variety of young members to participate in this seminar series, and the criteria for the speakers to be eligible are as follows. First of all, be an ISRM member, have a maximum age of 35 years or 40 years if a PhD degree was obtained in the previous 5 years, and have worked in rock mechanics and rock engineering for a period no longer than 10 years. The speakers' nominations can be made by the nominee's national group or by some other person or organization acquainted with the nominee's work. Self-nominations are also accepted. Nominations are to be addressed to the ISRM Young Members Seminar Series Organizing Committee. At the end of the presentation, you can also check this email here. And this webinar will be held every month, so we invite you all to keep in touch. Well, now I will give some guidelines on the organization of the seminar of this day. First of all, each presentation will last 20 minutes and will be followed by a 10 minutes of Q&A. And for the smooth running of the seminar, I would like to ask you to turn off your camera and microphone during the presentation. And if you have any questions, you can use chat and also use the raise hand feature. So let's move on with the first speaker. The first speaker is Dr. Kimi Sufuki, who is an assistant professor in the Department of Mining Engineering in the University of Chile, where she has been teaching and researching in the area of rock mechanics in 2019. Kimi holds a Bachelor of Science in Mining Engineering and a Master of Science in Mining from the University of Chile, and a PhD in Mining Engineering from the University of New South Wales in Australia. Her research focuses on the modeling of synthetic rock masses with application to cave mining and the study of post-peak behavior in brittle rocks. And today she will be presenting a talk entitled Numerical Modeling of Rock Masses in Block Cave Mining. Thanks, Dr. Suzuki, and the floor is yours.
Thanks, Ignacio, for the presentation. Give me 1 second. Yeah. So can you see my presentation?
Yes.
Okay. So I will start. So yeah, again, thanks again for the presentation. And today, the title of my presentation is Numerical Modeling of Rock Masses in Block Cave Mining. So my presentation is not the idea that this will be a lecture on numerical modeling. So maybe we can be talking about this for hours and having a whole course of this. So the main idea for my presentation is to talk a little bit of why we are doing this kind of numerical models and what's the main idea of this and why we are trying to do this. So for this, so I will start a little bit with the context, explaining what is block caving for the people who doesn't know this kind of method. So the idea of the method is that we have a block of a rock mass, the mineral ore, and the idea is to create an undercut level and an extraction level. And the main idea of this method is that we will cut this base of the block, and all the rock mass will start falling because of its weight. And this mining method is also combined with the effect of the stresses. So that's the main combination that will create these fragments, and that doesn't depend on the explosive. So that's the main idea of this mining method. And here we can see a very nice explanation and in this video. But the main limitation of this method is that today we don't have enough technology to really see what is happening. So in the video, I show you what we think that is happening, but actually we cannot be very sure about that. So that's a lot of interpretation of what we can do. So that's very challenging once we are doing this method, we are implementing this kind of method, because it's very important that we can predict what is really happening with the rock mass. So at the beginning, I mentioned that the title of the presentation is Numerical Modeling of the rock mass in block caving, but it's really important that we have an objective in mind when we are doing this kind of numerical models. And why it's important that we have an objective is not only the idea that we do a numerical model of what I'm showing you here, because maybe we can waste a lot of time, for example, doing a very specific model with a lot of nice colors that sometimes is very nice to see. But if we cannot explain or interpret what we have in the model, maybe the model won't be good enough. So here in this kind of method, we have a lot of uncertainties, and that's why it's very important for us to try to have a lot of understanding. So I want to go to the end of this video to show a little bit that here we can see that this kind of method also creates a substance in the surface. So if we try to see what kind of geomechanical problems we can achieve from this point of view, we need to be sure that this kind of rock mass will cave. So caveability is very important. The prediction of the caveability is very important. And also we need to be sure that we can also try to predict the size of the fragments. If we have very big fragments, that can become a very huge problem in the structural level if we think it from the operational point of view. And also the substance is very critical because maybe we can have some infrastructure there. So these are different problems that we can achieve from the geomechanical point of view. And it's very important to have some of them in mind if we are doing, for example, numerical modeling. So, so this is very briefly what the mining method is. And what we can do today. I want to explain a little bit what are the options that we have today for trying to predict the geomechanical problems that we can find in this kind of mining. So one of the methods that we have today is, for example, this lecture chart that is very popular, usually when we are, for example, trying to predict if the rock mass will cave or not. So this method was originally created in the 70s, and here we can see the last updates that are from the 90s. And maybe we can highlight a lot of, for example, limitations from this chart. But what I want to capture from here is that in this chart, you can see most of the caving operation that existed at this time. So as you can see, that's not much if we compare, for example, with other kind of problems that we can see, for example, in geomechanics, where you can have a lot of data, and maybe we can even, for example, use machine learning to try to have a very nice calibration between, for example, different responses. So I wanted to highlight this because this is not the case of most of the geomechanical problems. In this kind of problem that we are trying to define, we are usually we usually have very limited data. So here, each point represents one different mine. So in the world, actually, there's no many operating caving mines enough to have a nicer chart. So that's one point. And another important point that I wanted to highlight from this chart is that this chart was created in the 90s. And since then, most of the mines that are operating, for example, now, are working in very challenging environments. So now, today, we have a lot of mines that are working, for example, in more competent rocks compared to the ones that I'm showing you here. And also, most of them are working also in more complex stress environments. So that's also important to see, because all the mines that we are comparing, they may have different conditions, and that creates a problem that is very difficult to address if we don't have too many cases to compare with. So that's the context of this kind of block caving mines. And another point that I wanted to highlight is also this that I'm showing you here, that it's the caving mechanics. The other problems that we have is that as we cannot see everything that is happening in the mine, we are not very sure how the blocks are being created. So we are not very sure how all the fractures are propagating. So we have an idea of what might be happening, but as we cannot really predict what is actually happening in each point of in all the volume, that create a very difficult problem, for example, to calibrate in a numerical model. So this also adds a little bit of uncertainty to any model that we may be creating. So here I'm showing you a conceptual model that was proposed in 1999 that is very specific for stress caving. That is, stress caving is very specific for depending on the stresses that are around in the area where we are working. So this conceptual model is very useful because help us to understand which are the different stages that the rock mass will take from the in situ state until it gets caved in the extraction point. So here we can see all the different stages being compared with the failure envelope. So this is very useful if we want to, for example, create a numerical model, because we can use this kind of caving mechanism to try to calibrate this kind of model. But the main problem here is this is very specific. So not all the mines will have this kind of explanation for what you can see. So a more recent model that was proposed in 2018, it's called the Speculative Potential Extended Conceptual Model of Caving. And here the author proposed that we can have two different cases. So the one that I'm showing you in the right is similar to the one I presented you before. And the author also included another model that is the one at the left. So where you can find, for example, extensional fracturing. So these two extreme cases are cases that have been seen in different operations that are operating in different conditions. But the other problem we have here that we can have different factors that will create difference between two different mines. So it's not very easy to identify why we are seeing these two different responses. So what the author is proposing here is we have these two extreme cases, but we may also have something in the middle. So this work is very interesting because it's saying that we still don't have enough understanding of what is really happening in the mind. And as I said before, this is very critical if we are doing a model and we want to calibrate what we are seeing. So that gives us the context where we are working once we want to do, for example, numerical modeling. And if we combine all these elements I mentioned before, we can classify any kind of modeling problem in these 4 different classes. So this is very general for any kind of mining model that we are doing, or any model in geosciences or any other area. So we can classify a model, the modeling of a problem, in 4 different categories, depending on how much understanding we have and depending on how much data we have. So as I mentioned before, in this kind of geomechanical problem, in caving mines, we don't have much data and we don't have much understanding. So that limits us once we want to calibrate the model that we are proposing, because we can create a very good model, but if we don't have something to validate, that becomes that creates a problem, because we don't know if we can believe or not in what we're proposing. So in the other side, we also can have problems that where we can have a lot of understanding and also a lot of data. So that's the opposite case, and this may be easier, for example, to validate, because we can choose any kind of validation technique, and that will be enough for knowing if the model we are proposing is good or not. So here I superpose different problems that I think that may be different that we can find in mining. And in one extreme, at the right, at the top right, we can see that, for example, understanding the relationship between the fleet vehicle data and maintenance requirement is something that today we have too much data and understanding that we can even optimize this kind of problem. So that becomes a problem of optimization, and we can have a lot of data to try to all the time try to improve this a little bit. In the opposite side, where we don't have much understanding, but maybe we can have more data, is, for example, trying to predict the geometallurgical parameters from core scans. So here we can, for example, have data collected in real time, but we will still have, for example, the uncertainties because of the variabilities in the mineralogy, for example. And in the opposite side, we have all the mechanical problems. We don't have much data. We don't have much understanding. So that creates a problem once we want to validate this kind of problems, because we need to rely on all the conceptual things that we know about the problem. So that's create a complicated kind of model. And now, briefly, I wanted to explain what we can find today related to different numerical methods that has been applied for this kind of models of trying to model the block cave, the rock masses in block caving. So we can find a continuum method and discontinuum method. And what is interesting here is that we can find the first model in this that were developed in the 70s. And this is very interesting because this was the time where most of the classification systems were developed. So at this time in the 70s, most of these classification systems were developed collecting a lot of data from different mining operations and also, for example, civil applications. And on the opposite side, we can see also what kind of models were developed at the time, and they were very limited because of the computational requirements that we could find at the time. So if we see what we have now, we have the completely opposite side. So now we have very complicated models that can run very fast and try to solve very complicated models, compared to all the data that maybe we can get to create a case history, for example. So this is very interesting, the first models that we created. And in the 80s, we can see that we can find the first model that were created just to try to respond very simple questions. So for example, here I'm showing you a model that only tried to approximate which was the limit for the block movement. So that's also very interesting because the models at the beginning were very simple for very specific questions. And then we can see that in the 90s, a little bit more complex models were created. And these kind of models that are UDEC and PFC are very interesting because here we can see that we are trying to also understand the mechanisms that are happening, for example, between block and block. So we are trying to, here we can see that we can add more reality to all these kind of models. And finally, I wanted to highlight this in the 2000s, that we can see a lot of different models in different areas, and also some of them that were developed in other engineering fields that were applied to trying to understand this kind of models. So in this time, we can see that the first models that were created at the mine site size were developed, and that's very interesting because at this time was the first time that we could see a larger model trying to understand factors that maybe we couldn't replicate in previous models. So if we go to what happened after that, we can see that in 2010, we can find also other models that are giving more detail to how the rock mass is fracturing. So I can highlight this because here we are trying to approach more realistically how the rock mass is really fracturing. But the limitation of this kind of model is that they can still be applied only to a smaller size model, because that still takes too much computational time. And finally, what we can see today in the recent years is that a lot of constitutive models have been proposed for trying to replicate what is happening in the rock mass in this kind of caving mines. For example, we can use, for example, the conceptual model that I showed you before, that was proposed, for example, for the stress mining case. And we can apply this in all these methods that I showed you before that were developed in the previous years. And today we can find a lot of different options that are very specific for different mine sites that have been collecting a lot of data. So for example, one recent development that has been proposed by Itasca, for example, is this application using FLAG, where they couple also what we have in the IMAS constitutive model, also with a cave sim approach. So today we are seeing different approaches that are being coupled, and that can also help us to try to have very more complex and detailed model to try to understand this problem. But as I said before, remember that it's important that we don't have much data. So if we don't have much input data that is of good quality, that will mean that whatever we can interpret from this model maybe won't be so good. So it's always important to be very to have a lot of time to try to have good input data before start doing this kind of model. And just as closing point, I want to say that all this kind of continuum method, we can see today that they have application at mine site scale. So we can even try to model, for example, the draw strategy that we will have in the mine. And that's a very specific question. Remember, as I said at the beginning, you are not only representing the rock mass just because you want to have a nice model. You need to have a question that goes also with that idea. So if you want to use this kind of algorithms that are really good with a big mine size, you can use this kind of model because they can incorporate this constitutive model. But the main problem of this kind of continuum method is that there are some parameters from the rock mass that we cannot even understand in reality. For example, the post-peak properties are really important, and the models are very sensitive to those kind of properties. And if you cannot understand really good, that will have a real impact in your results. So that's one of the main disadvantages of this kind of method that are really sensitive to things that we are not very sure today. And then we also have this discontinued method that have the advantage that they are more realistic to what they can represent, especially in this kind of mining method where we are very interested in the fracturing of the rock. But the main problem is that we are limited with the time requirement, because this kind of method take too long, and they require also a very large computer requirement. So that's why, again, we need to understand very clear what's our question that we want to solve before trying to choose any of these numerical methods. And just as conclusion, I mentioned that this kind of problem is are very complex, because we have too many factors that are affecting in the mine, and we are not able yet to take a picture in the rock mass to try to validate this kind of model. So it's always important to take to have in mind that you need to be very careful once you are interpreting this kind of results. And another thing that I wanted to highlight is that usually after geotechnical disaster has happened, that has been the opportunity for us to try to create more understanding. As I mentioned here, we have a lot of advances in the technology in numerical models, but we don't have much understanding of what is really happening with the caving mechanism. So it's always important to highlight that. It's important also to have time to try to doing research and trying to understand that, because depending on that, that will be also the value that the models will have. And finally, I just wanted to say that this kind of model can be really useful to try to incorporate all the physics of the problem. So I think that this kind of models could be also very useful to try to create more understanding, specifically in this kind of very complex processes that is the caving mines. And that's my presentation. Thanks to all who are listening. I don't know if someone has any questions.
Thank you very much, Dr. Suzuki, for your excellent and interesting presentation. As you said, we have some 10 minutes for question and answer session, for a short session of questions, if there are any. Does anyone have any questions about this presentation? You can raise the hand. For example, Jennifer Day has a question.
Thanks, Ignacio. Thanks very much, Kimie. That was a great presentation and about the history of cave mining and modeling. I'm curious, what particular aspects of cave mining are you focusing on lately for your research?
Yeah, so I completed my PhD, and the main idea of the PhD was trying to propose a method based on numerical modeling to try to give you an idea of if your model, if your rock mass will cave or not, trying to get an option to all these caveability charts. So the main idea of what I'm trying, of my research, is trying to use the numerical model, but in very simple cases, to try to create a more general idea of the cases, to have a more general idea of what cases can be compared to your case. Because if you see, for example, the different caving cases, some of them have parameters that may be similar. So you don't have many, and some of the parameters are not very broad. So it's not as you're, for example, doing some experiment in the lab and you're preparing, for example, a solution that you can, for example, choose very extreme cases. So in caving mine, you cannot choose anything. You just have something. So my idea of using numerical modeling is to try to use the physics and try to create very general cases and try to get some conclusions from that.
Great, thank you.
Well, thanks for your question and for the answer, Jennifer and Kimi. Is there any question within the audience? Well, Fedilberto González has a question. Please, thanks. Proceed with your question.
Hi, Kimi. Thank you for your presentation. Given the fact that the uncertainty of the block caving is a problem that we need to overcome, have you thought about using mining-induced seismicity, which is the most reliable parameter that probably we can have when the rock is fragmenting? So have you thought about using this mining-induced seismicity, the hypocenter of this mining-induced seismicity and all the things that we can record to have a rough idea of what is really happening, where it is happening, and when it is happening, and to overcome the issues when the uncertainty that you have?
Yeah, that's a really good question, Fedilberto. So yeah, you said at the beginning that maybe we can overcome the uncertainty, but I think we need to assume that the uncertainties will always be there. It's something that we need to try to improve our understanding more than trying to solve those uncertainty, because it's what it is in the rock mass. And regarding the seismicity, there are some models that have been calibrated using the seismicity, but I think that's only one response from the rock mass. So, for example, if you are trying to for example, predict, for example, capability in another case, and you have a different level of seismicity, I think that's a response that is may not be good enough in all the cases. So, as I said before, in this model that represents the different caving mechanisms, in some cases, maybe the seismicity will be important and will be very good for you to calibrate the model. But maybe in other cases where you don't have much, maybe that won't be enough. So I think that you will always depend on the site where you're working. So maybe in some models that will be the response, but maybe in others it won't.
Thank you.
Okay, I don't know if there are more questions. No, I don't know if in the chat, but well, I have a question, Kimi, for well, after attending the presentation, and my question is about how do you model the post-peak behavior of the materials? And the question is about how to model dilation. I mean, are these state-of-the-art models about non-associated plasticity rules implemented in these numerical models you carried out, or how do you model dilation with these models, with these numerical models?
Yeah, that's a really interesting question. So, for example, you have different models. For example, you use these discrete models where you need to give the parameters of the rock and the discontinuities. There is today we don't have any model that is able to replicate the complete curve. If you're, for example, trying to calibrate a sample that you tested in the lab. So that's one limitation if you are trying to model just what you have in Interlock. So that's also a limitation that will be reflected when you have a bigger model. If you're, for example, using discrete element method. But for example, if you have this continuum method, you just need to set the dilation and the post-peak properties. So the problem is, as you don't know what is happening in the real rock mass, you are setting a parameter and you don't know if that's your reality or not. And this kind of parameters, for example, the post-peak behavior is very sensitive in the models that are continuing. So we still have a lot of challenges there because we still don't know what's happening in the rock mass. We can measure something in the lab, but we still don't have any model that is good enough for representing that behavior.
Okay, thanks for your answer. So I don't know if there are more questions. Well, if not, I think we can move to the next speaker. Thanks, Dr. Suzuki, for your presentation. Excellent presentation. So, well, it's Jennifer's turn now to follow with the next speaker presentation. Thanks.
Perfect. Thank you, Ignacio, and thank you again, Kimie, and to the audience members for your questions. So let me introduce the next speaker of this webinar session. The next presenter is Mr. Alexander Ramos, who currently works as a ground control engineer at underground mines in central Peru. He graduated as a mining engineer at Pontifical Catholic University of Peru in 2018 and took part in the ISRM program at TU Clausthal, Germany in 2015. His work has focused on optimizing ground support systems and geotechnical designs with regard to cut and fill stoping in burst-prone conditions and in deep mining. Recently, he is working on improving reinforcement, retaining and holding elements at a very complex seismic environment in a fully mechanized mine. Mr. Ramos, the screen is yours.
Thank you, Jennifer. Hello, everyone. May we share the presentation? If everything is okay, I can start. Let's start with the topic, the strategy and tactics for both spur condition in deep underground mine. I think it's a very special topic, but it's not like a lecture, as Kimie said. This topic is related with a real case here in Peru. With it's like a story how the mine comes from non-seismicity problems to give very, very complex seismic. So let's start with the agenda. Here, we start with the some keywords about support system, then rock burst terms, and then all the seismicity words. Then let's talk about ground condition site here, very specific. Also talk about mechanical properties of some interlocks here in the mine. Number 4, the evolution of the support system by rock burst inspection. My personal opinion here is the most important slide here in the presentation, and also the analysis and interpretation of the data, and the resume as tactic as strategic of the presentation. Let's start with some keywords here. First, ground support. Let's divide the ground support as Kaiser and KN Kaiser in 2018, like divide by roles. Reinforce, retain, and hold. It's important to understand or make difference of these roles, because when we compare some elements under rock burst, each of them reacts very different. Reinforce elements of support system which strengthen the rock masses and enabling the rock mass to support itself. That's right. Could be an example. It's a split set, common split set, or maybe a Swellex bolt. It's very common used here in Peru. Another role support, it's retain. Its function is transferring the weight of the fractured rock near the excavation to the holding elements. As you can see here on the top right figure, comes from K and Kaiser. Retain elements works as together with holding elements, which is the next role. Hold need to tie the retaining elements and reinforcement broken rock to stay stable. So let's take more. Let's understand that one of each role make a system. So each part of the system, it's important to all the system works very well. Then now I'll start with some keywords about rock bursts. The definition of rock bursts you can search in many bibliography, but I consider to put it the next, defining as damage and excavation that occur in a sudden and violent manner and is associated with the seismic event. I want to focus on the violent manner because most of the rock bursts here in the mine occurs, but no one can see because of the shotcrete we use here nowadays. However, another type of false asleep rock bursts now are occur in the mine, so it's important to make the difference of what type of rock bursts we are talking about. First of all, a strain burst, it's a sudden violent failure of rock near an excavation boundary. As you can see here in the left bottle of the previous slide, volume of rock push the shotcrete to the hand of and the lamp, as you can see in the photo. This is strain burst, and it takes in around 90% of the rock bursts here in the mine. So it's the most common rock burst here we have. The second one is pillar burst. Refers to damage to an excavation caused by an excessive loading of pillar, such that the pillar core fails violent. It's happened so few in a few occasions in very special areas here in the mine. If we talk about a number, could be 5%, no more than this, and it's very. We have controls in the mine to look what is the progressive failure of the pillar. And then the most important here, it's a fall slip rock burst. Here is the most important because the damage that can gives to the rock mass, sorry, to the ground support, refers to the damage to an excavation caused by energy release from shear or slip or shear rupture source. As you can see in the last photo here in the bottle side, right, fall slip, you can see a plane fall and the ground support was failed. This zone was abandoned because the surface area was was damaged for the rock burst. So then go ahead with more keywords about seismicity. Micro monitoring system. It's a passive observation of various scale earthquakes. As you can see in the image of the right, these spheres colored by different colors and sizes are the epicenter of the events here in the mine. In the photo, you can see principal fault that is delineated by huge moment magnitude events and followed by very low seismicity. Then another keyword, it's important, the device is geophones. We have in the mine triaxial geophones and uniaxial geophones, which is a device which converts the movement of the ground into voltage to record them in stations such as data logger or paladin. Another term important here is the seismicity induced by mining. So as we're talking about the mining activity, especially the mining method and the blasting process, is the most important thing here in the mine that causes seismicity. Many of our voice generated by the mining method as current field and sublevel stopping, and the blasting process cause the seismicity in the mine. Two important terms are resulted here are location accuracy. If you want to make analysis or very specific analysis on your data, seismic data, you need to understand what is your location accuracy of this position, because your source could be a fault, could be a pillar, could be a seal pillar, could be the face of your support. So you need to understand where is your seismicity. Detectability is the minimum seismic event that can be located by your monitoring system. If your monitoring system is not able to search very low seismicity, you need to only report huge seismicity, and it's not the goal of a seismicity monitoring system. And the last is seismic source. If you have good location accuracy and detectability, you understand good, or you have a hypothesis of your seismic source that could be pillars, faults, blasting, the layout of the mine, could be others. In the bottom side of the presentation, here is the simple array of geophone sensors here in the mine. We start with them with triaxial sensors, as we can see here in the photo, and uniaxial sensors. So let's talk more about ground condition outside here in the mine. As you can see here on the photo, we have a very important influx of water. So many of our operations are subjected to inflows, come from drill hole exploration and fractures of the rock, and also by faults. Another complication here is the complex structural models, because many faults govern the structural behavior of the deposit. As you can see here in the principal as a plan view, this is a basic design of our stopes, and you can see here the plane faults that are in the same way of the ore, so we can avoid them. And another important thing is the depth of the mine. The mine has erratic topo, vary of depth, and now it's around 1,000 meters below the surface and goes deeper now. Let's talk about now mechanical behavior, why rock bursts appears now and why now appears in the past. That's interesting question, because the mine is not the first time that goes ahead to this depth. 10 years ago, the mine goes 1,000 meters also. And why in this time they don't have rock problem and now we have? So let's take more about emphasis on the mechanical properties of interlock. As you can see here on the photo, triaxial tests were made recently here in the mine. Many of our results are only with 6, 9, and 9 confident stress gives around 250 MPAs. So if we maybe look at a very specific mechanical behavior of the rock mass, one can say that the material is very elastic, and that happens. As you can see here on the photo, in breccia texture on site, this material, it's unfracturated material. It's only foliated materials, like metamorphic material. Other material that we can here have in the mine is the breccia texture, that it's have a very low capacity to make rock bursts. So if you compare to sorry, we compare two textures, zebra texture and breccia texture. Zebra, it's more able to make rock bursts inside of them, and breccia material is not. Another thing we need to take attention is the young modulus of the materials of the same rock. We determined many young modulus comes from 20 to 30 gigapascals of the same rock. So this result describes the interpretation that we are doing. It needs more details. Could be the orientation of the core, could be the problem, or could be other thing. So understanding these materials, let's talk about rock burst inspection and evolution of the support system. As I told you at the beginning of the presentation, the support system transform evolution from welded mesh splits and bolts, like here on the photo, to welded mesh incorporated with structural microsynthetic fibers and welded mesh. Let's start with welded mesh and split set bolts. This support is very common here in Peru. Their cut and fill operation at sub-level operations. But the problem here is loosening of rock mass caused by seismic events around the excavation. So if we have you very active seismic events around the excavation and you support it's welded mesh and a split set, you invert more time in rehabilitator labors. What is the evolution from this support? The incorporation of steel fiber reinforced shotcrete with split set bolts. But what was a problem in that moment? That with split set bolts, the cracks on shotcrete was great and propagates along. And with the environment, with the problems with the water here, the fiber degrades in the time, as you can see here on the photo. So if we don't have problems with the water, steel fiber performs very well here on the mine. But if we have problems with water corrosion problems, so we decided to change steel fiber reinforced shotcrete to structural microsynthetic fibers. So continue to support. We use steel fiber reinforced shotcrete with more ratio of steel fiber and also incorporate swelling bolts to replace split set bolts. In the evolution of the support system, we reduce the aperture and propagate cracks on the shotcrete. But the problem was that with the reinforced shotcrete, the form of the metal, the form of the steel fiber was very silicon, so it loses its performance in the time under rockboards. So it will be replaced by structural microsynthetic fiber to tie blocks of shotcrete and non-corrosion issue experienced because of the material, of course. But the problem was to replace steel fiber with a structural microsynthetic. The Young modulus is very important because Young modulus of the structural microsynthetic fibers, it's around 1 and 10 divided by 10 of the steel fibers. That means at the same load, the shotcrete will be therefore more. So cracks will be more appearance in your labels. To overcome this problem, we incorporated again welded mesh as a retained element of the slab of shotcrete that could be appearance of the mine. So let's talk about now analysis and interpretation of the data. So that's around the area of interest. Here we have in the image, you are not able to see the labor because more of the events are spread around the mine hours. As you can see in the clock, from 6 to 7 and 18 to 19, most of the data are concentrated in these values. So what's happening if we filter this data and then put it on them and only select the events that are more huge or called also stronger motions? The relation is the same. From 6 to 7, which is the blasting hour, we have increase in the frequency of these events, and also from 18 to 19 hours, we have an increase on this. So what's the conclusion of this? Most of the seismic problem here in the mine comes from blasting. This is the main conclusion. So, well, how can we rely on them? We have a recall of all the blasts, all dates, every 2 parts of the date. So as you can see here, this is the blast. Let's take some picture. This is the recording of the blast, but this event is not related with the blast. It's a seismic event induced by them. So this is the conclusion from the analysis and interpretation of the seismic data. And what happened in the damage on the supposed system after blasting, it's frequently. As you can see here on the opening in the mine, the blast was here, and then we have damage as a bulking process in this part. So if we have this conclusion, what's the tactical rounds we adopted? First of all, we make a statistical analysis of trigger events, which comes from resting type of blasting and full phase of blasting, because we in the mine, we have two type principle of blast. So we have a statistical, and we search that 80% of the seismicity induced by blasting comes from this type of blast. So with this, another control is the examinate where is the sensible areas in the mine. As you can see here on the photo, this is a plan view of the stope. All of them have this type of blast. Could be here or could be here. So the decision is when and why. If we have a concentration in the max value estimation, for example, we decide to directionate the advance in that sequence, or maybe or not. This depends on the evaluation. If we have a max value increased, and also the even frequency in that zone, we increase the distance from blastings, maybe 20, 30, 50 meters, each of them. Another control that we made is to determine the optimal time to produce the wave destruction process. That means when some blasting material explodes, creates waves. So if we have here in the line as a wave, and then determining what's the time, T, in which wave the next explosive cause the destructive wave process of the wave to conclude that all the wave is destroyed, is that analysis. In the 5, 25, and 55 milliseconds of the time is the best position to produce destruction process of the waves comes from blasting. Another tactical control that we use is the distribution of the blasting time around the mine. All the mine have the blasting times, which is a period of time with the mine start blasting. But here on the mine, we have only 30 minutes. But in reality, most of the blasting are very near, could be 2 minutes separated each of them. So we distance this blasting, and then we reduce the seismicity as a tactical control. Let's talk about strategic ground controls. What happened with the concluda stoop? We use filling materials, but these materials are not so able to catch energy, because our filling materials in the mine are not able because its properties. We are now improving the mechanical behavior of the filling, incorporate cement to backfill using waste material. We are using waste material from our developments, the deepest developments, and use cement as a backfill of these stopes. Then also incorporate the disking classification on our core login, and then also put chain link mesh, with some areas of the mine, because most of all sleep rock boards are very aggressive in the damage on the rock on the chrome support. And another strategic control is to reincorporate the hardening behavior. As I told you, steel fiber is not the same as synthetic fiber because of Young modulus principle. As you can see here on this test, we have a peak on shotcrete, and then it would go down. With this is called softening process. It's very common with synthetic fibers, but if we have steel fiber, it could be the graph could be like here, and it's called hardening process. So this is what you're looking for now in the mine. So resume. First of all, make classification of support elements helps to understand the role of them and its bottlenecks. As all the inspection on rock boards we made, you need to make attention why and how your elements will fail. The second one is ground condition dictates your principal problems at depth, such as fall, water, and support system. Why? Because here on the mine, we have a very complex structural model, and faults are in the ore, so you are not able to avoid them. And also water. Water is a very principal problem to maybe change your support elements. And in order, it's concluded is back analysis of each support element of your system helps you to improve them by rockboard inspection. Yes, and these changes are made in the process of maybe 1 year to maybe and around 80 inspection on rockboards. The mine comes from non-seismicity problems to nowadays very high seismicity. And finally, the analysis and interpretation of the seismic data needs good quality information and a specific site, because the location of the events could be for the specific site here good, not for other side could be. Let's say if you have accuracy location of 20 meters, could be okay for a sublevel stopping operation, and maybe for room and pillar operation could be not. It depends of your site and your decision as a ground control engineer. So this is all. Thank you very much for your attention. If you have questions.
Thank you very much, Mr. Ramos, for your very interesting presentation. Now we have 10 minutes for the question and answer session. Does anybody from the audience have any questions? I see Ignacio has a question. Please go ahead.
Yes, thanks, Jennifer, and of course, thanks, Alexander, for your excellent and interesting presentation. I think this kind of presentations open the door to the relevance, to highlight the relevance of the empirical and experimental approaches, especially in mining and rock mechanics related to mining. But well, my question is about in situ data. Have you got, or are you collecting any in situ stress measurement, or do you know more or less what's the behavior, the approximate behavior in terms of strength and the formability of the rock mass?
Yep, nowadays we are doing in situ measurement of stress using hollow inclusion overcoating process. Now we have one station, but the station is only one. We are looking for at least 3 to interpolate a formula to could be determined in which position the stress. But we have now only this. We are now in the process of changing the compare what is the empiricism and compare with the numerical models that we are incorporating in a couple of months. But we have, as a result, we our principal stress is subhorizontal stress, which takes around 30 MPAs, if I don't remember very bad. 30 MPAs at the depth of 500 meters. Now we have a 1,000 meters, so we expected more. We expected more. Maybe in a couple of months I can share with you.
Okay, many thanks, and interesting data to take into account. Thanks, and congrats again for your excellent presentation.
Thanks, Ignacio, for your question. I hope, Mr. Ramos, I hope you are successful with installing a few more in situ stress measurement sites. Does anybody else have any further questions?
I do.
Please go ahead, Sevda.
So Alexander, have you guys doing any monitoring on the backfill performance? How good the backfill is done?
Okay, I understand that your question is about the backfilling. Yes, backfilling, right?
That's right, yes. And if you are doing any monitoring.
Yeah, the backfilling now is in process. We have the design with 5, 7, and 10% of cement. We use the waste material comes from the principal ramp. We use them to put it into the stops. Using it's like a mixer, but I don't have the name in English. But it's like put cement aggregate. It could be pumped into the stop. This is why we're using, we're proving that design in the mine. We are looking for compare with the even frequency of one area in specific before and after this backfilling.
All right, thank you, Sevda. Are there any other questions from the audience?
Hi, Alexander. Thank you for your presentation. Yeah, I have a question. So I noticed that you had a very energetic seismicity. I think that I saw something like a moment magnitude of 2. Please correct me if I am mistaken. So you are using a very soft support system. You are using split sets mainly. So my question is, have you thought about upgrading these support systems to something stiffer? You know, something which which is more difficult to deform, and so your remnant factor of safety is going to last more. So have you thought about using stiffer support elements?
Regard the support system, the previous, let's talk about 2 years ago, the support system was split set and welded mesh. Nowadays it's shotcrete with very special receipt to make very ductile shotcrete with steel fiber and also structural synthetic fiber with welded mesh. And also we are looking for hybrid bolts and K-bolting as a reinforced material, because as you can see on the photo, on the presentation, I put a fall slip rock burst. So this fall slip rock burst, the depth of the failure is depend of the surface, the distance from the surface to the fault. And it's, of course, could be more than 2 meters. And it's 2 meters is the common use length of the bolts here in Peru. So K-bolts and hybrid bolts are more able to support this kind of rock bursts. But if we talk about strain bursts, 90% of our rock bursts here in the mine are strain bursts. But the problem when we're talking about fall slip rock bursts are which are very huge damage or could be make huge damage. This is why we are including this type of reinforced either bolts, K-bolting, and chain link mesh in some areas which are around these faults in specific. Yeah, but yeah, we are doing this.
Thank you.
Excellent. Thanks, Fedalberto. Are there any final questions for Mr. Ramos? Yes, go ahead, Ignacio, please.
Yeah, just a small question, taking advantage of this Q&A gap. My question is about the measurements of the stiffness and strength on the rock specimens in laboratory, because if I remember well, you mentioned two ways of measuring in laboratory for your samples, using well, strain gauges, I guess, and the other method by extensometers, or I can maybe refer to LVDTs maybe.
Yeah, we prefer use strain gauges in the we are talking about elastic properties.
Yes.
But we have a problem with characterize the post-peak behavior of the material. If you are looking for characterize this post behavior, you are looking for servo-controlled tests. That we are doing this because you have results that comes from non-servo-controlled results are very different. The post behavior of the material gives what's the energy could be transferred in kinetic energy. It's very important here in rock-porous environments.
Yeah, I suppose you place the extensometer or this device, not the strain gauge, just attached to the specimen, or by touching the platens, because you will maybe find differences, and as I could check in the presentation, the values of the Young's modulus and everything was quite in parallel, were quite similar. So you got a good agreement, I mean, between the strain gauge measurement and between the LVDT measurement in your rock specimen. So that was just a small question. So thanks.
Thank you.
Perfect. Thanks, Ignacio and Mr. Ramos. I think we'll wrap it up there. I'll just share my screen and about the next seminar. So we have reached the end of this third ISRM Young Members Seminar. On behalf of the organizing committee, I'd like to thank the ISRM for helping us in the organization of this event. I would also like to thank Dr. Kimie Susuki and Mr. Alexander Ramos for their very interesting and valuable presentations that addressed two relevant topics in rock mechanics. We hope that this seminar provides you with new insights and new challenges for future research, and it could be a periodic event for sharing ideas about rock mechanics and related topics. For this reason, we would like to invite you for the next seminar that will be virtually hosted by our Australasian colleagues in April. Dr. Selahattin Akdag from Australia and Corinne Singeisen from New Zealand will present their works respectively on experimental analyses of burst type extreme rock failures and rock fracture under high stress conditions, and coseismic rock slope failure mechanisms, insights from landslides triggered by the 2016 7.8 Kaikoura earthquake. Further information about this event will be available on the ISRM newsletter and website, so keep in touch to not miss the next webinar. If you're interested in participating in this seminar series, please contact us by email at isrm.ym.seminar@gmail.com. Thank you again for your presentations, and to the audience for your participation, and have a wonderful and safe day.
Thank you, Jennifer, and thank you, Kimie and Alexander, for your excellent presentations and for the interesting questions. And thanks also to the audience who participated in this event. So, well, see you in the next seminar.
Thank you.
Bye-bye.
Bye-bye.
Thank you, everyone.
Thanks. Bye.